Hello everyone. In this session, we are going to see about an Dijkstra's algorithm. Have you ever wondered how Google Maps find the shortest route from your location to destination? So behind the scenes, it is very much powered by a very smart algorithm like Dijkstra's algorithm. And today we are going to learn how exactly it works. In this video, we will explore Dijkstra's algorithm, which is a very much powerful technique to find the shortest path in a graph. So you will understand the logic through this example. So let me start with the basics. So what is Dijkstra's algorithm? It is a greedy algorithm that finds the shortest path from a source node to the all other nodes in a weighted graph. But always the weighted should be in the positive. It should not be in a negative. It works repeatedly, picking the very much nearest unvisited node and updating the distance of neighbors until all nodes are processed. It will keep on repeating the repeatedly to keep on picking the very much nearest unvisited node and then keep on update the distance of the neighbors until all nodes are processed. So where we can find the real-time real-world application. This algorithm is widely used in all the navigation systems, in GPS, networking routings, social networks. Uh, these are the things where we are using this algorithm in the real life world. So now we will jump into the example and then we will see how this Dijkstra's algorithm works. So now let me consider this A as a source node. Let me consider this A as a source node. So distance of all vertices except source is infinite. You can observe over here because we are going to start from the A node onwards. So let me have an all the remaining nodes as a infinite. This is the first step. So now here from this A vertex, I need to find the shortest path to all the vertices. I can go directly to D by this way, or by to through B and D I can reach it, or through D straight away I can reach it. I can reach the G by means of A to B, B to E, or E to G, or A to D, or D to E, and E to G. So now we can reach the destination by many ways, but through Google Maps. But the Google Maps always give the shortest path. Okay. So now we will see how it happens. So now select the source node as A and check the neighbor nodes. So the neighbor nodes are B and D. Okay, because these are all the arrow marks are outwards. So always you should consider the outward arrow marks. So A to B is 2 and A to D is 1. So that is the shortest value, right? Previously it was infinite, but it has compared to infinite, the less values are 2 and 1. So I will take it. So now among this three nodes, which one is minimum? D is the minimum. So now uh, from D, where until I can go to D, I can reach E. I can reach E. So here the D value is 1. The D value is already 1. So it requires to go to E, I need to add two more value over here. And then to reach G, 1 plus 4, 5. To reach F, 1 plus 8, that is 9. Because I am finding the shortest path from the A to F, not D to F. So A to D is 1 and D to F is 8. So 8 plus 1, it's 9. F value is 9. Likewise, A to G is nothing but A to D plus D to G. 1 plus 4, that is 5. Likewise, A to E. A to D is 1 and D to E is 2. That is 1 plus 2, that is 3. So you can see here, distance of F is going to be nothing but A to D is 1 and then distance of D, that is A to D. Distance of D is 1 and 1 plus 8, that is 9. that is 1 plus 2, that is 3. 1 plus 2, that is 3. And 1 plus 4, that is 5. So now here among this, which one is minimum? 3395. Which one is minimum? So now already here we have 2, which is already less value. So the remaining vertices are here B, E, G, F, C. So 2, 3, 3, 9, 5. So 2 is the minimum. 2 is the minimum. So now we will consider the B node. So from B, I can reach the E with a value called 2 plus 10, 12. But I can reach the E through A to D and D plus E, which have a minimum value, that is 3. So I will ignore it. I will ignore it. And then I can reach the D directly from A to D as a value as a 1. But through A to B 2 and B to D is 3. So 2 plus 3, 5, which is larger value than the 1. So I will ignore it. So now we will consider the remaining vertices C, E, F, G. So which is the minimum value over here? C and E are the minimum. Okay, so we will take the E, because since we have taken a B as a previous, so we will consider neighbor node itself. So now here the G value is, so E is connected to only to the G. So already the E value is going to be 3. A to D and D to E is 3. And then 3 plus 6 is going to be 9 to reach G. But I can reach the G by directly from A to D and D to G with 1 plus 4, 5. But if I come through this way, I require the value as a 9. So then I can ignore this value itself. So next minimum is C. So to C, the only connection is F. So here already we have an corresponding value is, previously it was 9. Previously it was 9. A to D is 1 and then D to F is 8. It is 9. So now next value is C. So C value is 3. How is C value is 3? A to D is 1. D to C is 2. 1 plus 2 is equal to 3. 1 plus 2 is equal to 3. To reach C, I have a value called 3. And from C, it is connected to F. So 5 plus 3 is nothing but 8. So which is lesser than this path. So you can see here, if I come by this path, I need value called 9. If I come by this path, I need a value called 8. So then I prefer the path of this one. So I have the value called 8. So then F and G, which one is minimum? So 5 is the minimum. So here G to F is value is 1. G to value is 1. So now here, if I come by this path, I have the value called 8. But if I come by this path, the value is 1 plus 4, 5, 5 plus 1, 6. So 6 is lesser than the 8. So now I can replace with the value called 6 over here. And then the remaining node is F. In the F, all are incoming. No one is outgoing. So all the nodes are visited. All the nodes are visited over here with a minimum number of weight. Okay, so what's the weight to reach this G? I need a value called 5 only. To reach the F, I need value called 6 only. To reach the B, I need a value called 2 only. 1 minute. I will change this. So I can reach the D by directly. I can reach the B directly. I can reach the E through A to D and D to E. I can reach the G, A to D and D to G. I can reach the F, D, G, F. I can reach C, A, D, C. So this is how I can find the shortest path in the given graph. So where do we apply this one? The real-time applications are going to be Google Maps or network routing. And wherever you want to find the shortest path among the different routes, we can apply this Dijkstra's algorithm. Thank you.